All right, in this video we're going to talk about some of the properties of roots. All right, so I have up here already, like the first three of these kind of correspond to the laws of exponents, which if you haven't watched my video about the laws of exponents, you can check that out and see what those laws of exponents are. But in the last video that I did, where I just kind of introduced what a root was, what the terminology is, and what a root really means, I talked about how a root is really just another way of talking about the exponential relationship, right? So if you see that connection between the exponents and the roots, well, then it really should come as no surprise that some of the properties of roots correspond to some of those laws of exponents, because there is that connection between them, right? And that's one of the key things when you're learning mathematics, especially like higher level mathematics, seeing those connections between these different parts of it and how exponents and roots are actually related to each other, and how these three properties of roots are really kind of the same thing as a couple of those laws of exponents. When you see those connections, you start to get that deeper understanding of what's going on. It also makes it easier for you because if you don't see the connections, you just have a whole bunch of laws of exponents that you have to memorize and a whole bunch of properties of roots that you also have to memorize, plus all the other stuff you have to do. I mean, it's a lot of things to try to keep straight in your mind. But if you see how they're all connected, you start to notice, well, these rules are kind of the same as the ones I saw before for exponents. It's less stuff that you actually have to remember because you see that connection between them. All right, so it's one of the things I always try to promote is understanding those connections and how one part of math is connected to another part. It just makes it easier to kind of grasp everything that's going on. All right, so anyway, the properties of roots. The first one, the nth root of a times b equals the nth root of a times the nth root of b. All right, so if I'm taking the root of something that involves two things multiplied together, I can split those apart and take the nth root of each one of those things individually and then multiply those results. All right, similar to how we saw the laws of exponents when I had two things in parentheses, a times b raised to a power, I could split those apart or kind of like distribute the exponent to both of those things. Here it's almost like I'm distributing the root to both of those things inside there. Right, and that works just like with the rules of exponents. That works for multiplication and also for division. Right, if I have the nth root of a divided by b, again, I can kind of distribute that root to both of those things. It equals the nth root of a divided by the nth root of b. Right, so those two correspond directly to the laws of exponents that we saw. And the third one also corresponds, the nth root of the nth root of a. Right, so if I'm taking the root of a root, well, I can combine those into a single root, and I just multiply those index numbers, the m and the n. It is the m times nth root of a. Right, just like when I have a power raised to a power, right, an exponent raised to another exponent, I multiply those two exponents together to combine them into a single one. Right, when I have roots, same idea. I multiply the two root numbers that I have to combine it into a single root. Right, so those first three there correspond directly to some of those laws of exponents that we talked about. The last couple don't really correspond to the laws of exponents, but you can see they actually do involve exponents. They're the root of something raised to a power. And we use these properties here a lot of times when we're solving equations. If we're solving equations of like an x raised to a power, we use these properties here to kind of cancel out the exponent. All right, so the nth root of a to the nth power equals a if n is an odd number. Right, so if I have like an a raised to like a third or a fifth power, if I want to cancel out that exponent, I just take the third or the fifth root. Basically, whatever the exponent is, if I take the corresponding root, it will cancel out the exponent. Right, again, like I said in the last video that I did where I explained what roots were, I said that roots were like the inverse of exponentials. Right, so inverses cancel each other out. So if I want to cancel out an exponent, I take the corresponding root, it's going to cancel my exponent. Right, so it cancels directly if n is an odd number. If n is an even number, then the nth root of a to the n equals the absolute value of a. Right, and if you recall, the reason we have to have that there is because, remember, if we're taking an even root of something, our answer has to be a positive number. Right, so this absolute value of a here, remember, the absolute value makes whatever's inside there and turns it into a positive. Right, so this just ensures that no matter what that a was in here, when I take that even root, it has to come out to a positive. Right, so we do the absolute value of a. If a was already a positive number, then it doesn't matter. It just comes out to the positive number, just like this one up here. But if a was a negative number, this absolute value now forces it to be positive, because an even root has to have a positive answer. Right, so that's why that one has the absolute value. Right, but again, if I have something raised to a power, and I want to cancel out the exponent, I take the corresponding root, they cancel out, and we will see that as we proceed into solving algebraic equations and things like that. I'll kind of bring this up again when we get to that point so that you can kind of see where these properties of roots kind of come in. All right. So those are 5 properties of roots. I put another one down here. Remember, these ones up here that correspond to the laws of exponents. If I have multiplication or division inside my root, then that means I can distribute the root to both of those things inside there and kind of separate them. And the same thing was true for the laws of exponents. If I had multiplication or division inside of parentheses, I could distribute the exponent. But remember, with the laws of exponents, we said we cannot do that if we have addition or subtraction inside the parentheses raised to a power. In that case, we can't just distribute the exponent. Well, can we do that with a root? In other words, is the square root of a plus b equal to the square root of a plus the square root of b? Well, let's put some numbers in there and test it out to see if that's true. If I have the square root of 9 plus 16, is that equal to the square root of 9 plus the square root of 16? Let's see. So the square root of 9 plus 16, well, 9 plus 16 is 25. And the square root of 25 equals 5. All right, well, what's the square root of 9 over here? That's 3. The square root of 16 would be 4, and 3 plus 4 equals 7. And 5 does not equal 7. Right? So, again, just putting some numbers in there to show you that, while we can do this rule for multiplication and division, it does not work if we have addition or subtraction inside that root, just like it doesn't work for the laws of exponents when I have addition or subtraction on the inside. It's another one of the common themes that we'll see, doing algebra and doing precalculus. Some rules apply only to multiplication and division. They do not apply when you have addition and subtraction. Right? We've seen it already with the laws of exponents. We saw it already when we're dealing with some stuff with fractions. And we see it again here with roots. The nth root of a times b is the nth root of a times the nth root of b. The square root of a plus b is not the square root of a plus the square root of b. Right? If I have addition or subtraction there, I cannot split those apart and do separate square roots. And I bring these things up pretty often in the videos I do because they are really common mistakes that people kind of make all the time. Right? So you have to be real careful about when you are allowed to do certain things and when you are not. And if you're ever not sure, if you're trying to solve a problem, you see something like this and you're thinking to yourself, well, can I just make it do this? Well, throw some numbers in there like we did here and just kind of see if it checks out. Right? Even if you have like a calculator handy, you can just punch a couple numbers in and see, well, does this actually equal that? And when you test it out, you see it doesn't work, and then well, I better not do that. Right? Okay, so there's our properties of roots, a property of root that does not exist, right? The one here with the addition or subtraction. So I'm going to pause the recording here, and then I'm going to put up an example where we do a problem involving some of these properties of roots. All right, put a couple examples up here involving the properties of roots and just kind of working with roots and combining them together and things like that. All right, so the first one, the square root of 32 plus the square root of 200. Right, so it seems like the simple thing would be, well, I have 2 roots added together. Can I just add those together and make the square root of 232? No, right? We just talked about that. When I have addition or subtraction, I cannot just combine them together. It works for multiplication and division. Right? If this was the square root of 32 times the square root of 200, I can just multiply the 32 times 200 and put that underneath one single square root. But that does not work for addition. Right? So if I need to add or subtract radicals, the only way I can do that is if I have something like this. Like if I had like 3 square root of 3 plus 4 square root of 3, that's going to give me 7 square root of 3. Right? Since I have root 3's here, basically I just take those numbers in front and add them together. I have a total of 7 square root of 3's. Right? So if I'm going to add these together, I need to get it in a form like that where the numbers underneath the radical are the same number. All right, well, how in the world am I going to do that? Well, here's what we do. We look for perfect squares that will divide evenly into either 32 or 200 or really into both. Right, so my perfect squares, if I go off on the side here, right, 1 squared is 1, 2 squared is 4, 3 squared is 9. I should have written this up here before I started it. 4 squared is 16, 5 squared is 25, and so on. Right? I have 36, 49, 64, 9 squared is 81, 10 squared is 100, and that's about as far as I'm going to go here. All right, so those are my perfect squares. Now we'll look at the square root of 32. Do any of these numbers divide evenly into 32? There's actually a couple of them that do, right? 4 will divide evenly into 32, but so will 16, right? And we want to take the biggest perfect square possible, right? So I can break up the square root of 32 and write that as the square root of 16 times 2, right? Plus, and then the square root of 200, well, do any of these perfect squares divide evenly into 200? Yep, 25 does, but so does 100, right? 100, which is 10 squared, right? So I can write the square root of 200 as the square root of 100 times 2, right? And how does that help me, right? Well, what happens now is with the square root of 16 times 2, I can use that property of roots to say, well, that's the square root of 16 times the square root of 2, right? Remember, when there's multiplication inside that root, I can separate it into two different roots. And I can do the same thing with the next one. The square root of 100 times 2 is the square root of 100 times the square root of 2, right? And the reason I want to do that is because, and the reason I broke this up using these perfect squares, the 16 and the 100, is because I can actually take the square root of 16, right? The square root of 16 equals 4. So that's 4 times the square root of 2. And I can also take the square root of 100, that equals 10. So that's 10 square root of 2. And now I have two expressions here that have the square root of 2, and so I can add those together by just adding the numbers in front. 4 square roots of 2 plus 10 square roots of 2 equals 14 square roots of 2. So I get 14 root 2. That is the value, or the simplified form of the square root of 32 plus the square root of 200. Right? Going forward through higher level algebras and precalculus and stuff like that, you don't see this type of stuff a lot. But doing an example like this just kind of gets us in the flow of how to use the laws of roots and the properties of roots when we need to in order to simplify things and combine things together. Right? It comes up once in a while, but not that often. Right? But you have to split it apart, use your perfect squares, take the square root of the parts of it you can take the square root of, and then you can add them together when these root things, the root 2's, match up. All right, the next example up here, we have the square root of 49x squared plus 49. All right, so can I write that as the square root of 49x squared plus the square root of 49? I cannot, right? Remember, when there's addition or subtraction here, I cannot break those up into separate roots. It does not work that way. That only works if I have multiplication like I had up here, or if I have division inside the square root. Right, so what I can do here is kind of similar to what I did for these ones. I can factor this, right? Here I factored the 32 into 16 times 2. I factored the 200 into 100 times 2. And then I was able to separate them and take the square root of the part that I could take the square root of. Well, here, this 49x squared plus 49, and we haven't really talked about factoring yet. If you're watching these videos in order, we haven't gotten to factoring yet. But it's something we'll touch on soon. We can factor this into the square root of 49 times x squared plus 1. Right? The 49x squared plus 49, they have a common factor of 49. Right? And if to check that out, if you haven't done this type of factoring yet, to just check out that it's true, if you take that 49 and distribute it into the parentheses, 49 times x squared is 49x squared. 49 times plus 1 is plus 49. Right? So you get the same thing that you had up there. And the reason we do that factoring is because now that creates multiplication. All right, so this is another common thing that you see in a lot of different types of mathematical problems that as you move forward is, well, the rules, the properties of roots don't allow me to do anything when there's addition here, but there are properties that allow me to do things when there's multiplication. So somehow I need to change this addition thing into a multiplication thing. The way you do that is by factoring. Right? It comes up in all kinds of different contexts throughout mathematics. The rules only apply to multiplication, so I need to create multiplication by factoring, which is exactly what we did here, right? And once we factor that, now we can split it apart just like we did in that example up above, right? It's the square root of 49 times the square root of x squared plus 1, right? Since it was 49 times x squared plus 1, I can separate those, and the square root of 49 equals 7. So we get 7 times the square root of x squared plus 1. And that square root of x squared plus 1, there's really nothing more I can do with that. Remember, I can't break that apart into the square root of x squared and the square root of 1 because there's addition in the middle there. And there's nothing else I could factor out to try to create more multiplication. So that just has to stay the square root of x squared plus 1. All right, so those are a couple examples of working with the properties of roots. Remember, the key thing is knowing when you can do something and when you can't. Right? If I have multiplication, yes, I can split that apart. I have addition, no, I cannot split that apart. Right? And people try to do that all the time, which is why I've mentioned it I don't know how many times in this past 14 and a half minutes of this video. But it's a very important thing to know when you can do it and when you cannot. Multiplication and division, okay. Addition and subtraction, don't split those things apart. All right.